Okay, so today we have Suraj Malladi from Northwestern, who's, well, Kellogg, Mets, to be precise about the part of Northwestern he's coming from, which I think they're very careful about. And he's going to be talking to us about guarantees in price experimentation. So over to you, Suraj.
Great. Thanks, Jonathan. This is relatively new work. I'm very happy to be presenting it here. Please feel free throughout the talk to just jump in with questions and comments. Um, so let's get started. The question that I'm interested in here is a really basic one. It's how do or should firms set prices when they don't know their demand curve? Okay, and I'm calling this an Econ 101 question because it comes up fairly frequently when I'm teaching MBAs. So they'll typically say a comment like, look, in class, we're thinking about these problems where firms know their demand curve and they're nice and linear. But in practice, of course, there's a lot of uncertainty about firms' demands. Like if you think about, take the perspective of a startup, say, um, and of course, these demand curves can take on all sorts of wonky shapes. So, what relevance does the theory that we cover in class have to thinking about pricing in practice? And I think when you get a question like that, there's a few things you could say. One of the things that I say is that, well, in practice, firms have to experiment with different prices. And then over time, maybe they get a better sense of their demand curve, and that's going to help them converge towards an optimal price. Um, but this answer is not fully satisfactory because, in particular, it's silent on how exactly firms should experiment with prices, right? And there's a lot of different ways we can think about them doing it. You might imagine a firm starts at a high price and drops prices over time, or starts at a low price and raises prices over time, or maybe triangulates between high and low prices. Um, there's also a question of how big the step sizes should be as a function of everything that the firm's learned about its demand curve so far. Okay, so a lot of questions that aren't answered. And if you really wanted to get after it, a standard economic theory approach to this would be to say, well, let's think about a firm that sets prices every single period, and we'll suppose that this firm is maximizing its expected sum of discounted flow profits. And by characterizing such strategies, we have a prescription or a prediction for how such firms behave in practice. Okay. In this paper, I'm going to take just a slightly different approach. I'm going to think about strategies that maximize a firm's guaranteed sum of discounted flow profits. Okay. And there's a couple of reasons why you might be interested in an exercise like this. I think a normative interpretation is that in a lot of settings, firms might not even be able to quantify the likelihood with which they face one kind of demand curve over another. And in those sort of settings, it might be attractive to think about strategies that are robust in the sense that they give the highest profit guarantee. Okay. A positive interpretation would be that this, maximizing guaranteed profits is just an as-if description of ambiguity-averse firms. And by engaging in this exercise, we can make a predictions about how such firms behave. Okay? And I'll talk about one more reason for why we might be interested in this after I show you the results. So that's going to be the focus of the talk. I want to say just a couple more words about the standard approach before I move on. Okay. So price experimentation is a multi-arm bandit problem with correlated arms. Okay, so here each price is an arm. When you try a price, the reward you're going to get is that period's profit. And the arms are correlated in the sense that demand that you observe at one price is going to be informative about the demand that you observe at other prices. Okay, so if I sell something for $7 and I observe the demand that I get at $7, it's going to give me some sense of how much I would sell if I set instead a price of 750 or a set a price of 850. And what we know about those kinds of problems is that, except in very special cases, they're not going to be solvable not only analytically, but even numerically. Okay, so this gives sort of some difficulties with taking the standard approach. And that's left us a couple questions in the sort of rational price experimentation literature more open. So one question is, what is the path of experimentation that a fully forward-looking firm with a long planning horizon would take? And Merriman, Samuelson, and Urbano write that that two approaches have been taken to this question of experimentation in the face of a random demand curve. One is formulating an infinite horizon model in which the attention turns to the limiting expectation. And the second is restricting to two-period models. Okay? And here I'm going to be interested in thinking about a fully forward-looking firm. And I don't want to just sort of think about what happens in the limit, but I want to actually tell you something about how the firm's going to set prices every single period. Now, the first of these two approaches, so papers that take that approach are going to be interested in the question of, if you have a monopolist who doesn't know their demand curve, do they eventually converge to an optimal price? Okay. And they find some conditions on beliefs and the support of those beliefs under which it's true, and then some conditions in which you don't converge to the optimal price. And in those situations where you don't converge, you might ask, well, what's the extent of the mispricing, and in which direction do firms tend to misprice? That's, again, a difficult question to answer taking the standard approach. So Aghion, Bolton, Harris, and Julian is another classic reference in this literature. They write that when adequate learning does not obtain, one cannot understand the long-run outcome independently of the priors or the adjustment process by which it was reached. An entirely new kind of analysis is called for in these cases. And so to determine the long-run behavior of the agent, one needs to characterize the optimal learning strategy, which is possible analytically only in very simple learning problems. Okay. And one way to think about what I'm going to show you today is that it uncovers yet another simple learning problem where it's possible to shed light on the question of what is the path of optimal experimentation, and what's the extent of mispricing in the event that prices don't converge to the optimal price. Okay. So that's my introduction. So I'm going to sort of first give you a simple baseline model, and then I'll talk about the results and the proofs of those results. And then I'm going to generalize things a little bit later on, and conclude with a brief discussion. Okay. Good. So in the model, there's a multi-period monopolist. Okay, so time is discrete. And the monopolist faces a persistent demand curve D. And D is an element of some state space omega, and the monopolist doesn't know the demand curve. Okay, but she knows the set of possible demand curves omega. In this slide, I'm going to make assumptions about the state space. So let P naught and Q naught be some positive quantities, and let tau lower bar and tau upper bar be values lower than 0. I'm going to assume that omega is the set of demand curves, which are mappings from prices to quantities, for which D of P naught is greater than or equal to Q naught. Okay. And 2, the slope of this demand curve, if you measure it between any 2 points, is always going to be bounded between tau lower bar and tau upper bar. Right? And so the idea is that I'm here trying to think about a firm that knows very little about its demand curve a priori. Okay, so if you think about a startup that's introducing a new, say, protein-enriched cereal, what does this startup know? It knows that if it were to set a price of $8, like a lot of other cereal manufacturers do, that it would sell at least 10,000 units of cereal. So in my example, $8 is P naught and 10,000 is Q naught. Okay, and then it knows something about the range of elasticities in the cereal industry. So it's read some industry report, or it's looked at estimates from Aviv Nivo's paper on cereal. So it has some sense of what the bounds to elasticity are in this market, and it knows that if it set some focal price, it stands to make at least some amount in sales. But beyond that, it doesn't know a lot else about its demand curve. Okay, so it doesn't know that there's a bump here or a divot there.
Can I ask? I thought you introduced it as a monopolist. So how is there a rest of the market?
So good. So here I'm thinking about So you can think about a monopolist. You can think about a firm in a monopolistically competitive industry. So it's participating in an industry where there are other players. But I want to abstract away from sort of strategic considerations and focus only on the question of how do I optimally learn demand. Okay, and so you can sort of imagine an industry like that. Okay. What does the firm do? Each period, it's going to set a price, and it's going to observe demand at that price. Okay, so here, firm sets a price of D1 and learns demand at D of P1. So it doesn't actually know what this demand curve is. It has to set prices every period to kind of learn more.
Excuse me, did you, is continuity or something assumed or?
That's going to be sort of delivered by this assumption too, that if you take any 2 points, that the bounds of the slope is bounded between tau lower bar and tau upper bar.
Yeah, of course. Yes. Thank you.
Okay. In this model, histories are sequences of points that the firm has discovered so far on its demand curve. Okay, so price quantity pairs. And I'm going to use this notation omega sub h to denote the set of states that are consistent with what the firm has observed so far at a given history. Okay, so here the firm finds itself at a history where it's observed only one price quantity pair, P1 and Q1. Okay. And it entertains the possibility that the true demand curve looks like this dotted line that I've drawn through that point. Okay. It also entertains the possibility that the true demand curve looks like this curve. What it knows for sure is that the true demand curve can't look like this because this curve doesn't pass through the point that it's observed so far. So the way learning works in this model is the firm keeps discovering more points on its demand curve. And as it does that, it whittles down the state space to the set of curves that pass through all the points that it's discovered to date.
Can I ask a question, Suraj?
Yes.
You also mentioned this P0 and Q0, one of your
Yes.
assumptions. Where is that on this picture? Or does it
So
constrain?
that's not on this picture because P0, Q0 is not a point necessarily on the demand curve. All the firm knows is that if it were to set a price of P naught, it would make at least Q naught in sales. Right? So that's just part of the firm's prior information. That's just a characterization of the state space, not necessarily a point on the demand curve.
But potentially it can exclude some curves that pass through the demand point that is observed. So it is constrained.
Exactly. It excludes them. So if I drew P naught and Q naught, and I think that's going to show up in some later pictures, you have to make sure that the curve at P naught takes on a value that's Q naught or greater. So you exclude the curve there.
Okay, thank you.
Yeah. Okay. I'm going to use this notation H sub T to denote the set of histories where there exists some consistent demand curves. Okay. And I'll use bold H to denote paths, which are just infinite histories. What is a strategy? A strategy just is a fully contingent plan that says at every single history, the price that I'm going to set next. Okay. The way that I've have it written here, it's as if strategies are restricted to be deterministic. That's not the case. Everything that I tell you is going to be true, even if I allow for random strategies. But I'm saving myself some notation by basically focusing on deterministic strategies because it turns out that random strategies are not going to be optimal anyway. Now, a history together with a strategy and a demand curve are going to induce a path. So I'm starting at a given history where I've already discovered a few points on the demand curve. And if I consider if the demand curve is D and I'm using some strategy sigma, that's going to trace out some paths of price quantity pairs that I'm going to discover. Okay. The price path is going to extract just the price part of that and drop the quantities. And with that, I can talk about payoffs. So delta is my discount factor. The continuation payoff to any strategy at a history is just the sum of discounted flow profits on path. Okay, that's good. Which again, jointly determined by the strategy and the demand curve and the history that you're starting at. I'm assuming that marginal costs here are zero. Okay, so I've sort of dropped them from this equation. Everything's going to go through if you assume constant marginal costs or decreasing marginal costs. Now, at any history, we can say for any strategy, we can ask the question, what are the profits guaranteed by following this strategy? Okay, so starting at a history, I have strategy sigma. I ask myself, if I were to follow this strategy, how bad can things be? And the answer to how bad can things be is precisely this expression here. I take the worst case continuation payoff possible over all demand curves that are consistent at this history. Okay, so I don't have to worry about all possible demand curves. I only have to worry about the demand curves that are still consistent with what I've observed so far at this history. I take the worst case with respect to the set of consistent demand curves. That's what I'm calling the guaranteed continuation profit at this history. Okay. And I'm going to say that strategy sigma star is ex ante optimal if it maximizes the guaranteed continuation payoff at the empty history. So starting at the empty history, before I've set any prices, I consider every strategy. Each strategy is a fully contingent plan. And I ask myself, if I were to follow this strategy, how bad can things be? Okay. And the strategy that gives me the highest continuation payoff is what I'm calling ex ante optimal. Now, I want an even stronger notion of optimality, and to sort of describe that, I'm going to introduce one more definition. So for any strategy sigma, I'm going to say that history H sub t is reachable if it's either the empty history or it's a history that you could get to by following strategy sigma for some demand curve t. A strategy sigma star is sequentially optimal if it maximizes guaranteed profit at every reachable history. Okay, so in particular, a sequentially optimal strategy is also ex ante optimal because it has to satisfy this definition at the empty history. Okay. But more than that, a sequentially optimal strategy says, given the information that I've learned so far, am I doing the thing that guarantees me the best continuation profit? I'm interested in sequentially optimal policies because I want to think about strategies which are not only ex ante optimal, right? But I want to think about strategies where if you ask the firm at some random history whether or not it would want to deviate from the plan that it set out for itself initially, the firm would say, no, I'm happy following that plan because it's the best thing that I can do. So a firm
Suraj,
that
if I
eventually
may,
optimal strategy is rational in the sense that it sort of formulates a plan ex ante that optimizes some objective, and it wants to stick with that plan at every contingency. Yeah, Vince.
if I may, so what is this saying that, obviously while the firm is setting prices and experimenting with prices, it is making and losing money. So what we really want is a plan that it's not just doing experimentation haphazardly, it's doing this experimentation in a profitable way or a safe way or
Yes, and in
is
a
that,
way
is that
that's
what's happening here?
yes, and in a way that's also sort of fully forward-looking, right? So it's sort of
Right.
The firm is long-lived. It's solving this dynamic program, right? It's sort of saying that I want to use this strategy that gives me the highest profit guarantee and gives me the highest profit guarantee not only from where I stand today, but at every point in the future, no matter what I learn, following this plan is always going to be the best thing that I can do, the perspective of profit guarantee maximization. Are there any other questions about this? That's my model. Okay, so now let me talk about the results. So I'm going to define this strategy called the linear pricing strategy. The linear pricing strategy at every history constructs an artificial demand curve. So don't focus too much on this formula here because I'll show you pictures in a second. It constructs an artificial demand curve. And it says, for this artificial demand curve, I'm going to set the price that maximizes profits. That period. Okay. So this is how it looks in pictures. This is the true demand curve, say. At period 0, the artificial demand curve that the linear pricing strategy constructs is this. So this is a kinked, piecewise linear demand curve. The kink is at P naught Q naught, right? Above P naught, this demand curve has slope tau upper bar, and below P naught has slope tau lower bar. The linear demand strategy, the linear pricing strategy says at the empty history, I'm going to pretend as if this blue curve is the true demand curve. and I'm going to set the corresponding monopoly price, which is P1. Okay. Now, when it sets P1, of course, the firm learns that demand at that price is Q1. So what do you do period 2? You draw this kinked linear, piecewise linear demand curve through P1, Q1. Again, with the same slopes as before, tau upper bar and tau lower bar. You now pretend as if this is your true demand curve, and you set the corresponding monopoly price. That's P2, okay? At P2, you realize that demand is not D of P2, it's actually Q2. Okay, so what do you do period 3? Period 3, you draw this piecewise linear demand curve through P2, Q2. Okay, notice that at this history, you know for a fact that it's impossible for the true demand curve to be this blue kinked curve that I've drawn, because in particular, that doesn't pass through the point P1, Q1, which I already discovered was on the demand curve. Okay, but that's no matter. This is just an as-if description of the firm's strategy. Okay, and it's going to be memoryless. So you always draw this kinked demand curve through last period's price and quantity. You pretend as if that's your true demand curve, and you set the corresponding monopoly price. Proposition 1 is that the linear pricing strategy is sequentially optimal. Now, I'm going to define a notion of uniqueness. I'm going to say that the optimal strategy is essentially unique if for any two optimal strategies, sigma 1 and sigma 2, and any demand curve D, both strategies are going to lead down the same path. Okay, so if these strategies differ, they only differ at histories which aren't reachable, so it doesn't matter any. Proposition 2 is that the sequentially optimal strategy is essentially unique. Okay. And so together, these propositions sort of give, one upshot is that now when I'm asked the question, is there any operational value in solving exercises where firms have linear demand curves? One response I can give is to say, if you know how to find the optimal price for a linear demand curve, then you can actually trace out the profit guarantee maximizing strategy.
Okay, this is my question I was just about to ask.
So the next definition I'm going to make is I'm going to say that prices always rise under strategy sigma if for any demand curve on path, prices are going to be increasing over time. And similarly, I can say profits always rise if under strategies sigma, if for any demand curve, flow profits are always rising on path. Okay. Proposition 3 says that prices and profits always rise under the linear demand curve. So here's sort of one slide of interpretation, I think, at this point. So this is a very stylized model. It's giving a very stark prediction, and I think it sort of makes sense to step back and see if this prediction passes some sort of smell test. One piece of evidence that it does is that we see heuristics like this be recommended in practice fairly often. So if you go to the website of a venture capital firm like Y Combinator, they're going to suggest rules look like the following. So they have what they call the 10-5-20 rule. Basically, the idea is that every period you should keep raising price. If you're a startup and you don't know your demand curve, each period keep raising prices by 5% and do this until at one of those steps you experience a 20% decrease in demand. And they say when you found such a step, you found your optimal price. Okay. And if you talk to management consulting firms, they also suggest similar heuristics that involve raising prices over time. And they find that in their experience, when firms raise prices over time, according to their prescription, that profits are also going to be going up along the way. Okay. This looks sort of similar to what the linear pricing strategy is doing. The only difference is that the linear pricing strategy is not a heuristic. It actually has sort of an economic justification as the unique strategy that maximizes guaranteed profits.
When they suggest this, do they suggest it's going to be optimal or
I think no, there's no sense in which I don't think that they're calling it optimal. I think they're just sort of saying that this in practice is going to lead you to set better prices.
okay?
Right. Um, Another interpretation is that we can think of this as being just a really simple mechanism for rising prices. So if you go out and survey people and you ask them why is in general are prices of things going up, a very common answer that you get is that greedy firms are raising prices to increase profits. And this is a difficult sort of story to rationalize. And the reason is, if this greedy firm knew its demand curve from the start, then it should start at the monopoly price and it should stay at the monopoly price. And on the other hand, if the greedy firm didn't know its demand curve, then you would think that it has to experiment with different prices. And conceivably, this would involve sometimes experimenting with price hikes, but also experimenting with price drops. And as it's learning its demand curve, it sort of stumbles along the way and sometimes gets higher profits and sometimes gets lower profits. Okay. On the other hand, Proposition 3 sharply rationalizes this naive story because it says that if a firm doesn't know its demand curve and it's maximizing guaranteed profits, then optimal experimentation will necessarily involve rising prices and also rising profits every step of the way. And this happens despite costs and demand in this model being totally static. Okay, so it's a completely endogenous phenomenon.
I guess this depends a lot on the fact that you assume that they know the highest and the smallest slopes of the demand curve, right? So if you didn't know
That's right.
Right, you would probably need to reduce your prices if you find a steeper demand curve.
Potentially. So here what the firm is doing is it's sort of saying, I'm going to make very conservative estimates about how steep or how flat the demand curve can be. And typically, when we talk about pricing and people say, well, if I don't know my demand curve, how should I set prices? We say, well, at least let's start here. You know something about elasticities, right? You know that, elasticity is not too low or it's not too high. Let's start from there and pretend as if your, demand curve is linear and then set an initial price. That's a kind of heuristic that we often talk about, right? And for the firm in my model, that's all that it knows. And it's it sets so every time it experiments, it does so really conservatively because it's worried. Essentially what this kinked demand curve is expressing is that it says, if I were to raise prices beyond what I set last period, I worry that the demand curve is really flat and that I'm going to lose a lot in sales. On the other hand, if I were to drop prices, I'm worried that the demand curve is really steep and that I'm going to drop these prices, but I'm not going to generate that much additional demand.
Okay, and if you have the sharper that kink gets, the sooner the algorithm, kind of terminates, the faster you get to where you're going. And you stop earlier in some sense, I suppose, short of monopoly.
So that's a very good question. So that's kind of speed of termination isn't something that I have results on so far, and I think that's an interesting question to think about. But I'll tell you something about kind of how far you are from the monopoly price, and that's going to depend on the bounds for sure. So I'll show you a result that gets at exactly that, Jonathan. Okay. So far, the results that I've given you have to do with the path of experimentation. Now I want to show you something that's got to do with the long run. Okay, so where experimentation eventually converges to. So for any demand curve D and any optimal strategy sigma, prices are going to converge on path to some long run price, which I'll denote by P infinity D. Okay, so this experimentation path is going to lead to some price. I'm going to let P star of D denote the smallest informed monopoly price. So this is if the firm actually knew its demand curve, this is the smallest price that we would be happy to set, P star D. Okay, so P infinity D is where experimentation would lead me to. P star of D is the price that I would set if I actually knew my demand curve. Okay, I'm going to say there's underpricing if P infinity D is less than or equal to P star D. And then I'm going to say that there's price rigidity if at every history I set the same price. Okay? So I initially set some price and I stick with that price for the rest of time. Proposition 4 says that either depending on the parameters of the model, the parameters are, again, these tau lower bars and these tau upper bars, and then P naught and Q naught. Depending on the parameters of the model, there's either price rigidity or there's going to be underpricing. Okay. So if ever you find yourself in a situation where price is strictly increased on path, it's going to turn out that the price that you eventually converge to is going to be lower than any price that you would set had you known the demand curve. And the way I've written this proposition, underpricing is less than or equal to, but a sharper statement, which is true, is that generically you're going to be strictly smaller than the price that you would set had you known your demand curve. And here's the final proposition that I want to show in the baseline model. And Jonathan, I think this is going to get at your question. Now, I can ask myself, if I were to follow the guarantee maximizing price experimentation strategy, I would eventually converge to some price, and I would keep experiencing flow profits equal to P infinity times D of P infinity. On the other hand, if I knew my demand curve, I would experience profits P star D times dP star D. Okay, and I can ask myself, how far are the profits that I get from the profits that I would get if I'd actually known my demand curve? Okay, and it turns out this ratio is always going to be greater than or equal to 4 tau lower bar times tau upper bar divided by tau lower bar plus tau upper bar squared. So in particular, if tau lower bar equals tau upper bar, that's a world in which I exactly know my demand curve. Right? Because the lower bound on elasticity equals the upper bound, I know exactly what my demand curve is. In that world, this ratio is 1. Okay? So if I know exactly if I have no uncertainty about the elasticities, I'm going to set the optimal price already. But the wider is the range of uncertainty about elasticities, potentially the farther away I am in terms of flow profits from what I could be making had I known my demand curve. And this ratio is sort of telling me exactly how far I can be. Okay. And so I said in the beginning, I gave sort of a couple reasons why we might be interested in profit guarantee maximization. It's talked about how this is a robust policy for a firm that knows very little, and we can think about that as being a positive or a normative interpretation. I think a broader reason why you might be interested in profit guarantee maximization is you go to a firm, suppose it has some totally different objective than profit guarantee maximization. It might still be interested in knowing the answer to what can I guarantee myself in profits, right? What is a strategy that would deliver for me the highest profit guarantee? And proposition 5 sort of quantifies this, right? It says that, well, if this ratio is high, I go to a firm and I say, tell me what you know about elasticities, okay? And tell me what you know about some sort of lower bound in sales at a focal price. I will tell you what fraction of profits in the event you knew your demand curve that you could capture by following the price experimentation strategy. And if I were to tell this firm that, by the way, based off of the information that you gave me, if you followed the guarantee maximizing strategy, you could capture, say, 90% of the profits that you would get had you known your demand curve. Such a firm, even if its objective wasn't profit guarantee maximization, might say, oh, that sounds actually very attractive. I might consider doing a strategy like that. On the other hand, if you tell the firm, well, if you were to follow this strategy, it could only sort of give you a guarantee that you would get at least 30% of what you would make had you known your demand curve. The firm might say, well, 30% is not good enough. Potentially, I'm leaving a lot of money on the table. And so based off of the information you just gave me, it seems worthwhile that I go back and I do things like costly consumer surveys and market research to sharpen my understanding of what elasticities are in this industry. Okay. And so proposition 5 says that the answer to, how good is this guarantee might help the firm solve a meta problem of should it do more costly information acquisition to learn about its demand curve, or should it go ahead and implement the profit guarantee maximizing strategy? Okay.
When you say learn about elasticities, you mean about all the way along the demand curve, because they might not be constant, right? So
good. Yeah. So in this simple model, all I'm assuming is that, in a range of prices around the focal price, that you kind of know that elasticity is sort of, or slope is bounded above by some quantity and bounded below by some other quantity. Okay. You might imagine a state space in which these bounds are varying with prices. Turns out the results can accommodate state spaces like that as well. And when I talk about how the model generalizes, I'll get back to this. All right. So the proofs of those results are really simple. I'm going to do everything through pictures. Okay. I'm going to define a myopic strategy. So what does the myopic strategy do? At every history that you find yourself at, consider the set of consistent demand curves at those histories, at that history. Okay. D lower bar H is just the lower envelope of all the consistent demand curves at that history. So this is the lowest possible demand curve at every single price. Okay. And the myopic strategy, sigma lower bar, is going to do the following. At every history, it's going to pretend as if this lower envelope of all consistent demand curves is the true demand curve, and it's going to set the corresponding optimal price for that really conservative estimate of demand. Okay. Lemma 1 is that prices and profits always rise under the myopic strategy. And the reason for this is the following. If you are making this really conservative estimate of demand, then once you set a price of P1, if you're surprised by the amount of sales that you're making, you can only ever be surprised to the upside. The only surprise that can possibly happen is you sold more stuff than you thought you could, right? Never less, because you were very conservative about how much you were selling how much you could possibly sell in the first place. So if you're only ever surprised to the upside, then when you set a price of P1, you get these influx of inframarginal consumers. And that makes it attractive to raise price by $1 because you can now collect that dollar on more people. So you're always surprised. If you're ever surprised, you're only surprised to the upside. That makes it attractive to raise prices. Okay. But when you raise prices, you do so conservatively because you worry that the demand curve is very elastic. Okay. And so you set a price of P2. You're surprised to the upside again. Okay. And so this is what the myopic strategy is going to look like. Also, profits are going to be increasing every step of the way precisely because the strategy is myopic. A myopic strategy would only change its price if profits are going to increase that very period. Because you always have the option of sticking to the same price as before. And so that's why you have not only prices raising on path, but you also have profits also increasing on path. Okay. Lemma 2 says the myopic strategy, although it's not the same as the linear pricing strategy, it's going to turn out to coincide at reachable histories. Okay. And the reason for it is the following. So at this history, the myopic strategy draws this lower envelope of all consistent demand curves. Now I know by lemma 1 that once I find myself at this history, the next price I set, if anything, is going to be greater than P2. Okay. Now, if I lop off demand at this bottom part of the curve and straighten it out, a fortiori, I'm still not going to want to set a price lower than P2. Okay. So if I wanted to raise prices under this demand curve, I certainly want to raise prices under this demand curve. Here's the second case. I might find myself at a history that looks like this. Now notice at the empty history here, I wanted to set a price of P1. So I didn't want to be on this sort of upper portion of this dotted line, the dotted blue line. So at this history, after I set a price of P1 and I realized that I sold more stuff than I thought I would, it's kind of by a revealed preference argument, I still wouldn't want to set a price that puts me sort of on the hump of this demand curve. Because if that part of the demand curve was dominated at the empty history, it continues to be dominated at history H sub 1. Okay. So if I don't want to set a price that puts me in that region under this lower envelope of demand curves, I certainly don't want to set a price that puts me in that region when I iron it out. Okay. And so this is what allows me to basically just focus on this kinked demand curve at every single period. Lemma 3 says that the myopic strategy is sequentially optimal. Okay. And the argument is the following. So take any history and take any other strategy sigma. The myopic strategy is going to deliver a higher continuation payoff than strategy sigma in the event that the lower envelope of all possible demand curves is the true demand curve, right? Because if the lower envelope is the true demand curve, the myopic strategy is setting the corresponding monopoly profit. Conversely, for any history and for any demand curve, if I'm following the myopic strategy, the worst thing that can happen to me is that the lower envelope of all demand curves is the true demand curve. Why? If I were to face any other demand curve, all that could potentially happen is I make more in sales that period. But by lemma 1, I know that the profits that I would be making in all future periods would also be higher. And so if I faced any other demand curve when I'm using the myopic strategy, other than the lower envelope of demand curves, I'm weakly happier. Okay. And so this tells me that the myopic strategy and the lower envelope are a saddle point of the payoff function, and therefore, and because this happens at every history, the myopic strategy is sequentially optimal. Okay. So basically, proposition 1 follows from the fact that the myopic strategy is sequentially optimal, and it coincides with the linear pricing strategy on path. Proposition 2, the fact that it's unique, is going to be a function of lemma 1, which says that prices are increasing on path, and the fact that also that the initial artificial demand curve that I construct is piecewise linear and concave. Proposition 3, the fact that prices are rising and profits rising on path, just follows from the fact that this is happening for the myopic strategy, and the myopic strategy coincides with the linear pricing strategy on path. Okay. Finally, proposition 4 says that if prices were to ever strictly rise, you would only be weakly underpricing. And the reason for this is as follows. Here, I found myself at a history where I set a price of P1, I've learned demand at that price, and now I'm considering setting a price of P2. So under this artificial kinked demand curve, I would want to move from a price of P1 to a price of P2. If P2 is optimal for this kinked demand curve, then P2 is also optimal for the linear demand curve, because linear demand curves have a unique optimal price. But if P2 is optimal under this linear demand curve, that means setting a price of P2 is better than setting a price of P1 or lower for the true demand curve D. Because this linear demand curve has higher it dominates the red demand curve, which is the true demand curve that I'm facing at prices below P1. Okay, so what that tells me is that whatever the optimal price is, it certainly can't be lower than P1. And if you iterate this argument, it would tell you that kind of on path, the optimal price can't be lower than any price that you are willing to set. So the smallest optimal price that you would set, had you known your demand curve, must be greater than what you would reach by following the guarantee maximizing strategy on path. Okay. And a little bonus is that if prices were to ever strictly rise, it turns out that now you can get rid of the kinked part of the demand curve, because you would never set prices in the lower part of the curve anyways, and you would only need to draw the flattest possible linear demand curve through last period's price and quantity, pretend as if that's your true demand curve, and set the corresponding optimal price. And that's an even simpler characterization of the optimal strategy. Are there any questions about that? Okay. So that was the baseline model. And I think, some questions, a couple of the questions that I got were sort of questions about, what happens really if you were to change the state space that you are working with, right? So if you face a different set of demands, potentially with different elasticity bounds, would things still go through? So I want to now move to a more general model, which sort of relaxes the particular assumptions I made about the state space in the baseline case. Okay. One impression that the baseline case, the analysis in the baseline case might give is that basically having this worst case approach makes it so that the optimal forward-looking strategy coincides with the myopic strategy. And what I'm going to show you here is that actually that's not always the case. You're going to need sort of more conditions on the state space for that to actually be true. Okay, so let me give you a simple counterexample. Suppose that I actually know a ton about the demand curve. The state space consists of two linear demand curves. I know that whatever demand curve that I'm facing, it's got to be one of these two linear demand curves. Okay, so I have a binary state space. The myopic strategy, again, takes the lower envelope of the two linear demand curves, okay, and sets the corresponding monopoly price. I'm going to assume that the parameters are such that the myopic strategy says the optimal price is precisely where the kink of these two linear demand curves happens. I'll let RJ denote the corresponding monopoly profits of setting the monopoly price for linear demand curve 1 and linear demand curve 2. And I'm going to suppose that R1 is greater than R2. So let me just show you this in pictures. Here I have a binary state space. Either I'm facing the orange demand curve or I'm facing the purple demand curve. The monopoly price, if I'm facing the orange demand curve, is P upper bar. Okay. And the monopoly price, if I'm facing the purple demand curve, is where the purple star is located. Okay. And P naught, which is where the kink of this lower envelope of these two demand curves is arising, I'm going to assume the parameters are such that P naught is the price that the myopic strategy would set. Okay. Now, essentially, the argument that I'm trying to make here is that if you're sufficiently patient, the myopic strategy of setting a price of P naught every single period is not going to be optimal. Why? When you set a price of P naught, you don't learn whether you're on the orange curve or the purple curve. Okay? If instead of following the myopic strategy, you set a price slightly above the myopic strategy, you would immediately learn which curve you're on. And period 2 onwards, you could set the corresponding monopoly price, and that's a profitable deviation from the myopic strategy. Okay, so this is an example where the myopic strategy is not going to coincide with the forward-looking strategy. Okay. In fact, you can characterize exactly what the sequentially optimal strategy is. The exact expression isn't important. What's important is that now the strategy actually depends on this discount factor delta. The more patient you are, the larger experiment you're going to make initially. So if delta is closer to 1, you're going to set a price farther away from P naught. And if delta is closer to 0, you're going to set a price closer to P naught. Okay. And so this is going to be a world, again, where the sequentially optimal strategy doesn't coincide with the myopic strategy as it did in my baseline model. Right? One sort of intuition for why things are different here is that in my baseline case, there's a lot that you don't know about the demand curve. You knew these bounds to elasticities and this sort of lower bound on sales at some price. But beyond that, you don't know anything. You entertain this really rich set of possibilities for what the demand curve could look like. And in the face of this sort of extreme uncertainty, you say to yourself, learning is really hard in this world. And that's going to be a force that pushes me to care more about the present period rather than future periods. And any learning that happens is going to be purely incidental. On the other hand, the binary example that I just showed you is a world in which I know a lot about demand. It's either this curve or it's the other curve. In a world where I know a lot about the demand curve ex ante, a little experimentation is going to teach me a lot. It's going to tell me exactly which demand curve I'm on. So that's going to be valuable. And in a world where learning is very valuable, the myopic strategy is not going to coincide with the forward-looking strategy. Okay, so that's a kind of informal intuition for why we're getting different results between these two cases. Let me give you a sharper and more precise characterization. So I'm going to say that a set of strictly decreasing demand curves is a state space if both omega and the set of inverse demand curves, omega, which I'll denote by omega inverse, are uniformly equicontinuous. Okay, and let me remind you that being uniformly equicontinuous means that for any epsilon, there's a delta such that if I set prices P1 and P2 within delta of each other, doesn't matter what the true demand curve is, the difference in quantities is going to be within epsilon of each other. That's what it means for this family of demand curves to be uniformly equicontinuous. And then I'm going to assume that this set is also closed under the supremum norm. Okay, so what does this assumption of uniform equicontinuity really mean? It's just a generalization of the assumption that I was making before on kind of knowing bounds to elasticities, right? It says, regardless of which demand curve I'm on, I know that if I change prices by a little, that quantities can't change by too much. And that has to hold true regardless of what the true demand curve actually is. Okay. I'm going to say that a state space omega is downward closed if at every reachable history under the myopic strategy, the lower envelope of all consistent demand curves is itself also a consistent demand curve at that history. Okay. I'm going to say that omega is effectively downward closed. So this is a slightly weaker condition if at every reachable history and under the myopic strategy, there is some consistent demand curve where the monopoly profits I would make under that consistent demand curve is exactly equal to the monopoly profits that I would make had the true demand curve actually been this lower envelope. If omega is effectively downward closed, sorry, if omega is downward closed, then it's certainly effectively downward closed, but the converse need not hold. Okay. So again, downward closed is a very simple idea. It just says at any history, I take the consistent demand curves, I take the lower envelope, and if that lower envelope is also an element of the set of consistent demand curves, then I'm saying you're downward closed, okay? And being effectively downward closed is just a slight relaxation of that. My main theorem is that if a state space is effectively downward closed, then a myopic strategy is sequentially optimal. And conversely, if a state space is not effectively downward closed, then for a sufficiently patient firm, the myopic strategy is not going to be sequentially optimal. Okay, so this gives me a characterization of all state spaces where the myopic strategy is sequentially optimal, and those state spaces for which the myopic strategy is not going to coincide with the sequentially optimal strategy. Right? And the proof is if omega is effectively downward closed, then the fact that the myopic strategy is optimal is just going to be the same saddle point argument as before. In the event that omega is not effectively downward closed, you have to look at a history where this condition fails. You're going to then let M be the infimum of the monopoly profits you could achieve under any demand curve that's consistent at this history. You can use the Arzela-Ascoli theorem to conclude that the corresponding profit M is going to be greater than the profit you would achieve had you actually faced the lower envelope of demand curves. And whenever there's a gap between M and M lower bar, that's going to tell you that experimenting on a fine enough grid of prices is going to eventually lead you to discover a price where the flow profit is strictly greater than M lower bar. And if you're sufficiently patient, it will be a profitable deviation from the myopic strategy for you to experiment on such a fine enough grid. which is why the myopic strategy can't be optimal in those situations. Okay, so let's go back to applying theorem one. In the case where there was a binary state space, this is a situation where the lower envelope of demand curves is not itself a demand curve in the state space. So, right, the state space consists of two linear demand curves. The lower envelope is this kinked thing. That's not itself an element of the state space. So it's not down, this state space is not downward closed. Not only that, it's also not effectively downward closed. So there's no demand curve in the state space that would deliver the same monopoly profits as this kinked demand curve. And therefore, theorem one is going to tell us that the myopic strategy is not optimal in this case. On the other hand, if I made an assumption that omega is the set of all concave demand curves that satisfy my initial assumption one in the baseline model, I know that the lower envelope of all concave demand curves is also concave, right? So this is a state space that's downward closed. And so that immediately tells me that the myopic strategy is optimal for such a state space, right? In fact, I can give it the exact characterization of the optimal strategy. It's going to be very similar to the linear pricing strategy, but then you have to sort of make some modifications for the slope of these kinked demand curves in the event that your initial price is below P naught. Okay, so you can derive exactly analogous results to the baseline case in the world where you also know, in addition to some bounds to elasticity, that the demand curve is concave. If the state space instead consists of the set of convex demand curves, so you knew that the demand curves were convex, now here's a situation where the lower envelope of demand curves is not itself convex. So, right? So the lower envelope of convex demand curves is not going to itself be convex. So this is a state space that's not downward closed. However, it turns out that this state space is effectively downward closed. Okay, and so again, you're going to have analogs of all the same results by theorem one to the baseline case. And basically, what's happening here that's different than the binary example, this is my, the lower envelope of all convex demand curves satisfying certain slope bounds is not itself convex, right? However, I can rationalize setting a price of P naught because P naught is going to be optimal for a demand curve that is in the state space, which is convex, right? That's what it means to be effectively downward closed. And that's why the myopic strategy continues to be sequentially optimal in the case where I'm facing the set of convex demand curves satisfying certain slope bounds. Okay, and you can do it at other histories too. So this history, I can draw this linear demand curve through this price, and I can rationalize setting that price. However, this linear demand curve passes through the lower envelope, and so this is not actually an element of the state space. So my first attempt at rationalizing the price P1 failed, but this is a demand curve that is convex and lives in my state space, and for which the optimal price is going to be P1. Okay, so again, this is just a proof that in the case where we're facing the set of linear, in the case where we're facing the set of convex demand curves, the state space is effectively downward closed. Okay, so let me just wrap up. What I tried to do here is have a model where I can start with credible assumptions about what a monopolist knows about its demand curve, and I can derive policies that maximize profit guarantees and have results that sort of quantify when those guarantees are good enough. And so this was sort of a broader interpretation for why we might be interested in profit guarantees. And this is a slide that just mentions some of the literature on rational price experimentation. There are papers that focus on long-run learning, going back to Rothschild, and Easley, and Kiefer, and Aghion. These papers are concerned with what happens in the limit. So they don't characterize the path of optimal experimentation, but they're able to answer sort of non-constructively whether or not optimal experimentation will lead you to choose a price that the informed monopolist would choose or not. Another way people have made progress is by focusing on the binary state space case. So demand curve is one of two different curves. in that kind of world, if I'm experimenting and there's some noise in experimentation, what does optimal experimentation look like? Okay, and by comparison, I'm trying to sort of work with state spaces that make credible assumptions about what the monopolist actually knows about its demand curve. There's a literature that looks at 2-period models, and then there's also a large literature in operations and computer science that considers a variety of different heuristic pricing strategies with attractive long-run properties like low asymptotic regret. By comparison, I'm looking at a strategy that's in some sense exactly optimal. And so, if your solution concept is something like low asymptotic regret, that might deliver a strategy that's sort of useful in practice if you want to converge quickly to an optimal price. On the other hand, it doesn't make any prediction about firm behavior. And the reason is because you can take a strategy that gives you low asymptotic regret. You can do crazy things for the first trillion periods and then implement that strategy, and it has the same low asymptotic regret, right? So you actually have to work with a model where the firm is exactly optimizing some objective and doing so in a dynamically consistent way if you want to make a prediction about behavior. And that's what I was trying to do here. Okay. So I'll end there. Thanks for listening, and if there are any questions, I'm happy to take them.
Okay, thank you very much.